Hello everyone. We are the fifth group consisting of Wei Cheng Huang, Rohit Pokuri, Arya Suprana, Alan Lin, and Eric Mejia. Today we'll be explaining the techniques of integration. To understand the techniques of integration, we must first understand the definition of integration. So what is the definition? Well, integration is the area underneath of a graph. Let's look at some examples to examine some ways to estimate the area underneath a graph. Let's think about how we normally find the area. For a rectangle, we multiply the width and the length. Now let's think about finding the area underneath this graph from the x-coordinate 0 to 2. We can estimate the area underneath the curve by finding the area of some rectangles underneath the curve. Here are 5 easy steps to finding the summation of the areas. First, find the endpoint, which we'll label B, and subtract the starting point, which we'll label A. Then divide the result by the number of partitions, which we'll label N. This will give us the width of each rectangle or partition. Second, find the boundaries of the partitions. In other words, find each x-coordinate pertaining to the rectangles. In this case, they are 0, 1/2, 1, and 3/2. Third, plug in the x-coordinates into the function to find the respective y-coordinates of the rectangles, which are the heights of the rectangles. In this case, we get 0, 1/4, 1, and 9/4. Next, we find the area of each rectangle by taking the width of each partition and multiplying them individually by their respective heights. The areas of the rectangles are 0, 1/8, 1/2, and 9/8. Finally, we take the sum of each area that we have gathered. The result is 1.75. The result is an estimation of the area underneath the curve from x equals 0 to x equals 2. In our first example, our rectangles are underneath the line. This means that our estimation is an underestimation. This is because we used the first x-coordinate of each rectangle. In this next example, we'll be using the second x-coordinate of each rectangle, which will result in an overestimation. For our first step, our width remains the same, 1/2. In our second step, our boundaries are shifted over because we are using the second x-coordinate of each rectangle. Instead of 0, 1/2, 1, and 3/2, we have 1/2, 1, 3/2, and 2. In our third step, we plug in these boundaries to get 1/4, 1, 9/4, and 4 as our heights. The areas of the rectangles are 1/8, 1/2, 9/8, and 2, which results in the sum of 3.75. As you can see, the result is an overestimation. To make our estimation more accurate, we must increase the number of partitions within our given domain, 0 to 2. As you can see, as we increase the amount of partitions, we decrease the size of the gaps that we miss between the rectangle and the curve. So we let the number of partitions equal n, and we use the same 5 steps, this time modifying them to accept more partitions. In the first step, we find the width, but this time we leave n as a variable. In the second step, we'll give an index to each boundary. This way, we can use a formula to find each x boundary in a large set. In this formula, a is our starting x coordinate. I is a constant representing the index we are inspecting. Delta x is the width. Because in this case, our starting point is 0, a is 0, so we can write the formula for this case as 0 plus I times 2 over n, or just I times 2 over n. The third step remains the same. We plug in our boundary to find the height of the rectangle. In this case, it looks like this: I times 2 over n squared. This results in a formula for any given index: 4 over n squared times I squared. In the fourth step, we find the area by multiplying the width from step 1 and the formula for the height that we got from step 3. This results in the formula 8 over n cubed times I squared. In the final step, we take 8 over n cubed times the summation as I goes from 0 to n of I squared. As we know, the summation of I squared is n times n plus 1 times 2n plus 1 over 6. So we get 8 over n cubed times n plus 1 times 2n plus 1 over 6. The precision is dependent on how big n is. If we want to find the exact area of the curve, we find the limit as n approaches infinity. So now that we found the formula of the area, we can give it a new notation. This notation, known as the integral, represents the limit as n approaches infinity of the summation from the first index to the nth index. We can rewrite f of xi as f of x, and delta x as dx. F of x represents the height, and dx is the width. Now that we understand what an integral is, we can start talking about the techniques of integration. As it happens, calculating the integral is the inverse of calculating differentiation. Let's look at an example of a basic integral. Basic integrals are the direct result of differentiations. We know this because integrals are the inverse of differentiations. In this example, we are taking the integral of secant squared x. But as we know, secant squared x is the derivative of tangent of x. So we can say that the answer to the integral of secant squared x is tangent of x. However, we have to acknowledge that the differentiation of tangent of x plus some constant will also be secant squared x. So the answer that we will go with is tangent of x plus c to represent some constant, which can also include 0 if there wasn't a constant to begin with. Let's look at another example of a basic integral. In this example, we are finding the integral of x from 0 to pi over 4. Because we know that the differentiation of x to the power of n is equal to nx to the power of n minus 1, we can reverse the steps to find that the integral of x to the power of n is x to the power of n plus 1 over n plus 1. Looking at a graph, we can see that if our domain wasn't at 0, there would be a gap before our integral. So we take the integral up to the maximum of our domain and subtract the integral up to the minimum of our domain to isolate the area that we are solving for. The result is pi over 4 squared over 2 minus 0 to the power of 2 over 2. This is equal to pi squared over 32. The next technique is called U substitution. With U substitution, we take an equation and substitute U in to simplify the equation into something we recognize. In the following example, we have 2e to the power of 2x. We know the integral of e to the power of x, so we can substitute 2x out for u to resemble the form of e to the power of x. But we have to be aware that when we do the substitution, we also need to change dx in terms of du. In this example, we let u equal 2x, so du is equal to 2dx. We see that in the original problem, we can isolate e to the power of 2x to be e to the power of u. The remaining 2 dx will equal to du. This gives us a basic integral e to the power of u, which is e to the power of u plus c. Now we can plug 2x back into where we have u. This gives us e to the power of 2x plus c. The third technique is called integration by identity. In this example, we know that tangent squared x is equal to secant squared x minus 1. Because integration is a linear operator, we can separate this out into two integrals, the integral of secant squared x dx minus the integral of 1 dx. Now we can get tangent x plus c minus x plus c. Because the two c's are constants, they will add up into one constant. The last technique that we will discuss in this video is integration by parts. In order to understand integration by parts, we must first look back on the product rule for differentiation. As we can see from the product rule, we can rearrange the product rule and integrate both sides to get a formula that resembles the integral of f of x dx. This is the formula that we will be using for integration by parts. Let's look at an example. Here we'll use the formula to let part of the equation equal to u and the other will equal to dv. Let's let u equal to x. The remaining e to the power of x times dx will be equal to dv. From here, we can take the differentiation of u so that du equals dx. Notice that we still need a v. We can find v by taking the integral of dv. Doing so results in v equals e to the power of x. Now we can insert what we know into our formula. The integral of u dv is equal to uv minus the integral of v du. So the integral of x e to the power of x dx is equal to x times e to the power of x minus the integral of e to the power of x dx. Now we can take the integral of e to the power of x dx. The final result is x times e to the power of x minus e to the power of x plus c. When we are integrating by parts, there's something that we need to keep in mind. When selecting the part of the equation to be u, we have a hierarchy. We first prioritize inverse functions. These include sine inverse of x, tan inverse of x, and even ln of x. The second group we prioritize are polynomials, such as x, x squared, or x cubed. Lastly, we will choose sinusoidal terms and exponential terms, like sine x, cosine x, or tangent of x. Thank you for sticking it through with us. We hope you learned a lot.